So welcome back guys for question 2 and the last example.
Okay, so in this example we have a simply supported beam which has to carry a factored ultimate load of 215 kilonewtons as shown in the figure. As you can see, the 215 kilonewtons in the figure at point B and point C. So they say do not consider the self weight of the beam. Okay, so now the beam is laterally and torsionally supported only at points A, B, C and D. Okay, so now they say for this beam that we are designing for, we are checking this beam if it's adequate. So we are going to use this selected beam of 203 times 133 times 25 I section with a grade of steel of 350. So the first question, they want you to classify. Remember the previous example, we were just selecting, we selected and then we classify. This one we go straight to classifying. But to do that, we first have to go through the first step that we went through for the first example. Okay. So now you take your diagram. This is my simplified diagram. So now I'm going to find the reactions again. Again, this is symmetrically loaded. You can use sum of moments to find your reactions, but this, since it's symmetrically loaded, the loads are equal. So I know this is going to carry this 15 kilonewton, and D is going to also carry 15 kilonewton. So this will be 15, this will carry 15. So now they are all 50. Okay, so now we are going to find our shear force diagram again. So shear force diagram, we're going to start at A, it pushes up and then it closes at B, and then there is nothing between B and C, and then now you will have this much force there. So this is your shear force diagram in kilonewton. So now you draw your bending moment diagram. So the bending moment, I'm going to stand at B, this point B, this point C. I'm going to stand at point B and look at everything on my left. What I have on my left is the 15 times the distance of 4, which will give me 60. So that's my value of 60. Again, this is symmetrically loaded. Use a ruler to draw this. Symmetrically loaded, and then it will close there. So this value is 60. So this is the bending moment diagram in kilonewton per meter. Okay, so now I can say that my maximum shear force is 15 kilonewton, and my maximum bending moment, MU, it's 60 kilonewtons. Okay, so now we go to number A. Number A wants us to classify the section. Number A says classify the section. Remember, the section is a 203 times 133 times 25 I section. So classification. So we have the flange, which will be a B over 2TF. So you look for your I section on your steel design table. So now we have, this is the section that we're going to design for. You can see it, I'm going to highlight it in red. Okay, so my B here is what? My B is 133.2. So my B is 133.2 divided by 2 times my TF, the thickness of the flange is 7.8, which gives me 123.2 over 227, which gives me 8.54. Okay, so now I check. I go back to my code book again. Now I want to know, is it a class 1, class 2, or class 3? So for class 1, we check 145 over the root of 350, root of fy, which will give you 145 over the root of 350, which gives you 7.75, which is less than 8.54. So it's not a class 1. It's not a class 1. So you go back to your table. You check class 2. Class 2 is 170 over the root of 350. What does that give me? 170. It's 9.09, which is greater than 8.54. So the flange is class 2. Okay. So now you check your web. The height of the web over the thickness of the web. So the height of the web is 172 over the thickness of the web, which is 5.7. 172 over 5.7, which is 30.18. So now we check again. You remember for webs you use for class 1 you use 1100 over the root of fy, which is 350. So it's 1100 over the root of fy, 350, which is 58.880, which is greater than 30.18. Therefore, the web is a class 1. So the question wants you to classify. Now you have a class 1 and a class 2. The conclusion here I'm going to give is to say that the section is a class 2. Why? Because we designed for the more critical. We designed for the more critical one. If you move from, remember, as we move to class 4, it gets critical. So if you have class 4, you remember we don't. It requires special attention because it's more critical. So for between class 1 and class 2, the more critical one is class 2. So your flange is a class 2. We're going to design for a class 2, not a class 1. Okay. So from there, now you come to the moment capacity. Moment capacity. I'm going to use a new page for that. Now we'll calculate the moment capacity. The moment capacity Okay, so now another thing you need to note is where are you going to find the information on your code table, on your code book. On the code book, remember for the previous example where it was fully laterally restrained, we went to use information given in 13.5. But this time we have a beam that is laterally and torsionally supported only at points A, B, and C. So it's only supported at A, B, C, and D. So it doesn't provide continuous support. There's no continuous support. There's no continuous support. It's only at points A, B, and C, and D. So now we are going to have to use 13.6 to find our moment resistance. So our MCR, our moment resistance. Before I even go through this information, because you first have to find your your MCR in order to find all those other conditions. So my MCR, first I'm going to say that I'm going to cut this into segments. Ne? I'm going to take segment A to B. Why? Because this beam, it's supported at between A and B, ne? And it's supported between B and C, and it's supported between C and D. So I'm going to deal with my calculation in segments. I'll divide it into segments. There's not like a simply supported beam where there are no supports in between. So now I'm going to separate it. I'm going to take segment A and B. So for segment A and B, I'm going to say, if I can just note down the formula for MCR, which is your W2 pi over your KL, your effective length, and then it says EIY GJ plus pi E over the KL squared IY and then C down. Okay, so now we need to, all this information is given inside the table. The only thing you need to calculate is your W and your K, which you can also find on other tables. So we all know, we are given that W2 is on the code book. We are given that W2 is 1.75 plus 1.05 K. This is the small k, this is small k plus 0.3 K squared. And this value must be less than 2.5 for unbraced length subject to end moments. Okay, so remember, for between A and B, if I can just, between A and B, this is A, this is A, and this is B. Between A and B, you can see that the moment diagram gives you a triangle. This is A, this is B, and here you have 60. So the moment the moment diagrams gives you this kind of shape. So now we are going to use this information to find our answer there. So it says that K is, this W is 1 when the bending moment at any point within the braced length is larger than the end moment, okay? Or when there is no effective lateral support for compression flange. And so for our case, we are going to say that W equals to, we're going to say that our W equals to 1.75 plus 1.05 K plus 0.3 K squared. So, but for my K, I'm going to say it's 0 over 60. So my K is 0 over 60, which will give me a 0. Remember, they say that it's the ratio. K is the ratio of the smaller vectored moment to the larger vectored moment. Okay, so that's your value there, so you get 0. So now I'm going to substitute this into my equation, and I'll get W2 as 1.75. Okay, my K is 1. My K is 1, and then now the L is given. You come back to the information given. Between A and B, it's 4 meters, which is 4,000 millimeters. So now I can substitute all this information into my equation. So now I'll say that M, let me get another page. So my MCR will be, remember it's W2, which is 1.75 over, okay, pi divided by K, which is 1, and then the length is 4,000. The root of the grade, the modulus is 200. Even if you are not given, you can always know that it's 200 times 10 to the power of 3, and then as a conversion, and then now you times it by your IY. So now that you're going to get from your still table, this is Y, and then you're looking for this VL, so it's 3.09 times 10 to the power 6. So it's 3.09 times 10 to the power 6, and then you times it by your G, which is 77, and this one is, it's also standardized, 77 times 10 to the power 3 times J. You get it from your table, which is 59.0 times 10 to the power 3. Okay, so now plus open bracket pi times 200 times 10 to the power 3 divided by 4,000 times 3.09 times 10 to the power 6 times CW is 29.5 times 10 to the power 9. And then now you're going to find the answer for this substitution. So I'm going to just write the answer then. The answer is 99.15 kilonewton per meter. Okay. So this is your MCR. Now you come back to the code book. What does it say about this MCR value? It says that for class 1 and class 2, when MCR is greater than 0.67 MP, you use this equation to find the moment of resistance. Number 2, if your MCR is less or equal to 0.67 MP, you use that equation there. And then for number B, this is for double symmetric I section, like your I section. It's class 3 and class 4, so we're not going to use class 3 and class 4. We're going to stay here for class 1 and class 2. So now you calculate your MP. MP is ZPL FY. Okay, ZPL FY, which in this case is going to be the ZPL. You take the one for X. So the ZPL for this is what, 259. You take it here. It's 259 times 10 to the power 3. You times it by your grade of steel, which is 350, and then times 10 to the power minus 6 as a conversion. So yeah, this one can just confirm is 259 times 10 to the power 3 times 350 times 10 to the power minus 6. So this gives you 90.65. Okay, that's your moment. It's kilonewton per meter. So now we found our MP. Now we have to find, because remember it says 0.67 MP. 0.67 MP. So we need to find 0.67 MP, which is 0.67 times 90.65. And then this will give you times 6.67. This is 60.74 kilonewton per meter. So now you check. MCR in this case is greater than 0.67 MP. Okay, so that's our conclusion there. So now we come to the code book. We check. It's going to be MCR, which is greater than 0.67. So now we're going to have to use this equation to calculate our moment resistance. So this equation says that the moment resistance equals to 1.15 phi MP 1 minus 0.28 MP over MCR. But this value must not greater than MP. It must be less than your phi MP. That's the condition on the code book. It says not greater than phi MP. So whatever value you get there, it must not be greater than your phi MP. Phi MP, okay, we didn't calculate phi MP. So now MCR is 1.15 times 0.9 times our MP, which is 90.65, open bracket 1 minus 0.28 times 90.65, divided by our MCR, which is 99.15. Okay, so what value do we get there? 1.15 times 0.9 times. Okay, so we get what? 69.8 kilonewton per meter. So now we have to check, is it less than our phi MP? Phi MP equals to 0.9 times our MP, which is 90.65. Okay, 0.9 times 90.65 is 81.59 kilonewton per meter, which is greater than 69.8 kilonewton per meter. And now to check, remember our design moment is 60. We are designing for 60 this meter kilonewton per meter. We are designing for 60 kilonewton per meter. So this, our MR is greater than our MU. So this section is okay, or it's adequate.